it is a section 3.4, Hermite interpolation. So far, we tried to construct interpolating polynomials using function values. But for some applications, we may construct polynomials using function values and derivatives. Once the derivative values are involved, then the interpolation is called Hermite interpolation. Here we begin with basic concepts of Hermite interpolation. For example, we need to construct a polynomial of least degree, which means simplest polynomial, that interpolates a function f and its derivative at two distinct points, x0 and x1. Then the polynomial p should satisfy these four conditions. Here, for 2 points, they are x0 and x1. Here, function value and derivative, which is slope, and value and slope. There are four conditions. The polynomial should satisfy these four conditions. So possible choice is a cubic polynomial because we have four conditions. Now, we start with this form of a polynomial, the cubic polynomial. Then we have to decide the coefficients A, B, C, D. Now, because the information conditions are along with the derivative, we differentiate it to get p prime here. Then we use x0 and x1 to get these four equations. Once x is x0, then these all terms will disappear except a. So we have this one. Now, for this one again, if x is x0, then only limit term is b. When x is x1, then with the definition h is x1 minus x0, we have that portion from the right side. And when x is x1, we have that one. Now, a and b are already determined. Here, this is given data information. And once a, b are decided, then here c can be easily obtained. And again, finally, d can be decided. So we finalize the desired Hermite polynomial. Okay. Now we have here Hermite interpolation theorem. Once the function f is continuous up to its derivative, and we have x0 to xn, n plus 1 distinct points, then the unique polynomial of least degree interpolating f and f prime at the n plus 1 point, here that is the point, is the Hermite polynomial of degree 2n plus 1 given by this equation. Here we have n plus 1 points, and function value and derivative values are given. So we have 2n plus 2 conditions, so that here the polynomial we can construct has degree 2n plus 1. Here hn plus ni and hni hat are defined here, and lni is the ith Lagrange polynomial of degree n. You learned this one from earlier. Moreover, if we assume f is sufficiently smooth, then the error between the underlying function and the Hermite polynomial is given in this range. Now, here degree of a polynomial is 2n plus 1, so that remainder must be here for f 2n plus 2 derivative evaluated at some point, and 2n plus 2 factorial, and we have this product. In the standard interpolation error theorem, that is simply x minus xi product. Now, for each point xi, we are using the information twice, f values and f prime values, so it is squared. So you can memorize this formula quite easily. This is the theory. So we will not use this formula to get Hermite polynomial. You can do it, however, it'll be much more complicated. Now we'll try to construct the Hermite polynomials using divided differences, not using this formula. You can use this formula, but it's complicated. Okay. In order to construct Hermite polynomial using divided differences, we recall this, the polynomial Pn that interpolates f at here n plus 1 distinct points is given in this form. Now this one is C0 and 0th divided difference at x0, and these are basically this and these are diagonal entries of the divided difference table, and that is the Newton form of interpolating polynomial. Here we have a strategy for the construction of Hermite polynomial. In the beginning, we define a new sequence z0 to z 2n plus 1 which are duplicating xi. So yeah, for this first one, z0, that is same as x0, and again z1 is same as x0, and z2 will be same as x1, and so on. Here x values are duplicated. Then the Newton form of the Hermite polynomial can be given in this range. Now here, if you are trying to construct the divided difference table, then you will mean 0 over 0, because of duplication, 0 over 0 terms, then that can be replaced by the corresponding derivative. We'll see the details here. Now, and also we know that, and here the derivative f prime at xi is obtained through this limit and of the quotient f of x minus f of xi over x minus xi, and x is now approaches xi, so that rather than here limit, anyway, this xi can be replaced by xi and now xi, so that this quotient 0 over 0 is now around this derivative. So from the definition of derivative, we can roughly say that this 0 over 0 is now can be written by this derivative. let's see here. If we try to use Newton's divided difference technique, then here now for new sequence z values and z0, z1, so that there are 3 points right now, x0, x1, x2 for this example, and the function value and derivative values are given for 30 points. Now for new point sequence, we have here z notations. z0, z1 are the same as x0, and z2, z3. So we have a block here, 30 blocks. Now z2, z3 are the same as here x1, and z4, z5 is the same as x2. And again here, f values, which must be now f of x0, f of x0, and f of x1, f of x1, f of x2, f of x2. Now we try to get first divided the difference here, then this difference divided by that one, which is 0 over 0, so that we may consider that one as here, and one is now rather than the x0, that is x and that is x, and very near to x0, so that this the quotient can be written as approximately f prime x0. So that consider this one, I'll be different from x, I'll be perturbed points, then here this quotient is really around f prime x0. Okay. Now for that one here, this value difference divided by that one, we start with a distinct points so that bottom is non-zero, so that as usual you can write down here first divide the difference. Now we have again 0, the difference 0 divided by here 0, so that we are using now again derivative at x1. For that one here, bottom is non-zero, so that we put here dd1 in usual way, and in the last here now 0 over 0, so that we are using the derivative. And for remainder part, now if you try to get this one, then these two difference divided by x1 minus x0, so that there's no 0 over 0 term, so that as usual you can finish the divided difference table. So here we have a note, each 0 over 0 is replaced by its corresponding derivative value, while other divided differences are obtained as usual. That is the strategy to get Newton form of Hermite polynomial. Let's try to solve this example. Use the extended Newton divided difference method to obtain a cubic polynomial that takes these values. Okay, here, so that we start the divided difference table. There's x value and f value here. Okay, now that is x0, so that this x is 1 over x is this one, and then so this is x0 and x1. So here we duplicate, 0 is duplicate, x0, x0, x1, x1. Now function value, there's 2 and 2. At 1, the function value is now -4, -4. We duplicate in this way. Now we try to get the first divided difference. Okay. This difference divided by that, 0 over 0, so that it must be here f prime at 0, which is the same as here minus 9, right? And this is now subtraction is minus x divided by 1, so that minus x. And this one is 0 over 0, so that must be same as f prime at 1, which is now f prime at 1 is 4. Okay, we finished the first order divided difference. And now, from now on, we do as usual. So here difference is now 3 divided by 1, so that there's a 3. This difference is 10 divided by 1, so it's 10. Now that's DD2. And then DD3, and divided by, okay, subtraction is a 7 divided by 1, so that we have a 7. So this is the first coefficient, second coefficient, third coefficient, the final coefficients. So we can get this way. It's 2 minus 9 of x. Okay, we are using right now here, that is, okay, we write down here T10 h3 of x. That is, the first coefficient is 2 and minus 9 x minus x0, which is 0, and here the next coefficient is 3, and that is x minus 0, that's x0 squared. And then finally here the coefficient 7, that is now x minus 0 squared and x minus x1, which is 1. Okay, so we simplify this one to become this one. Okay, so this is the Newton form of Hermite polynomial. To construct Hermite polynomial, we can use the divided difference table construction method, and diagonals will be the coefficients. Here, this point is related with 0, and again that one, 0, so that you start with x minus x0 and x minus x0 squared, and then finally we are putting x minus 1 here. That's exactly same as for a Newton form of standard interpolating polynomials. Okay. Now this problem is the continuation. Find a quartic polynomial, fourth order polynomial, that takes values given in the preceding example, that values, and in addition satisfied at 2, the value is 44. So it is saying that function value is 2, function value at 2 is 44. Okay, let's try to add here. Now point is 2 and function value is 44. For this one here, earlier we duplicated for the points, but for this point we cannot duplicate because only function values are given. There's no derivative is given, so that we cannot duplicate this point. Just by using this one more row in the table, we try to finish the construction of the table. Okay, here 44, then subtraction 48 divided by 1, so that this is 48. Now subtraction is 44, now divided by 1, right? Now this is 34, the subtraction is 34, now divided by 2, so that's 17. Subtraction is 10 divided by, here that is 2. So that is 5. So the extra term is along with the 5. So that you have to add here now the extra 1, and that is plus 5, and here x minus 0 squared, and then x minus 1 squared, one more of x minus 1. And so that is the Newton form. By adding this one here, it will become now P4, fourth order Hermite polynomial in Newton form. Okay, that's the end of the section. Thank you.